Rohr. I'm a scientist at Spavor Systems Center Pacific. Some of the stuff I get to do is try to understand why dolphins swim so fast and all that kind of neat stuff. And I'm here with my colleague here today.
Hey guys, I'm Jess. I'm a mechanical engineer at San Diego State, and I've been building a Baja dune buggy for my club, and we're having a little bit of problem with vibration. So I wanted to talk to Dr. Jim over here with what is a vibration?
Let's talk about vibration. So it's not so easy, but let's sort of think about it. A scientist might say a vibration is a wiggle in space and time. You buy that?
No.
All right, let's think about it a little differently. Suppose you think of a guitar and you pluck a guitar string. That guitar string goes back and forth, back and forth, back and forth. Okay, that's a vibration, right? We sort of have an idea what a vibration is. And you can see if you took a snapshot of it, there'd be a wave on that string, right? That's my wiggle in space, that wave. And in time, because it moves back and forth, that's my wiggle in time.
Okay, so how do you measure this wiggle in time and wiggle in space?
So the wiggle in space is called a wavelength. And you might think about this if you're on the ocean, right? And you see waves. The distance between two crests of a wave, right? The wave might look something like this. The distance between those two crests, that's a wavelength.
Okay, so that's the wiggle in space. What about the wiggle in time?
So the wiggle in time would be if you're on a boat in the ocean and the waves are coming by, right? You're going to start bobbing up and down, up and down. Every time a wave comes by, you move up and down. So you sort of have a natural frequency. That frequency, that's the word for it, it's measured in something called hertz, and it's just how many times do you go up and down per second. It's cycles per second.
Okay. So does everything vibrate then?
Good question. Imagine if you drop something like this. This is just a piece of metal. It makes that sound because it vibrates. But now imagine dropping something like spaghetti. Does that make that sound?
No.
So something like spaghetti doesn't vibrate because it's not elastic. Many things like your bones and metals are elastic. So you can think of them as a bunch of little springs holding the atoms together. And when they're hit, they tend to vibrate.
This is aluminum bar, right? So it's elastic.
Yes, ma'am.
So if I hold it and hit the end, it's going to vibrate and make a ringing sound.
Give it a try.
But it didn't work. Why not?
It didn't work because you have to hold it in a special spot to get those natural frequencies to vibrate. You have to hold it at a node. The node is in the middle.
The middle.
Try that.
Okay.
Now, what do you think is going to happen? If this is
ring.
going to work?
It's going to ring.
If it rings, that means we've actually excited one of those natural frequencies.
Okay, so I totally get it now. So you're saying I have this aluminum rod and it's elastic, right?
Yes.
And I can hold it and hit it at the end, and by hitting it at the end, it's going to have vibrations and it's going to ring.
Try it.
Try it. Okay. Oh, it didn't work.
You have to hold it in the middle. Because when you hold it in the middle, that's a node. That's a part that's not vibrating in this wave that you're creating.
Let's
Try it again.
Oh, wow, it totally did work. That's awesome.
Yeah, so what's happening is we have this wave going back and forth, and it interferes with each other. And so it makes a standing wave. And because you have a standing wave, there's parts of the wave that's not moving at all. If you hold it where it's moving, right, it can't move, can't have a wave there. So that's why you have to be careful about where you're holding it. So when you hold it in the middle, what you have is a half wave, standing wave on this rod. So for example, if you wanted to calculate how fast the speed of sound in the aluminum rod is moving, remember we just have to multiply the wavelength times the frequency. Well, when you hold it in the middle, the lowest frequency, that wavelength is going to be twice the length of the bar. So you can easily measure the length of the bar.
Yeah.
Multiply by 2, and now you have your wavelength when you're holding it in the middle. Now to get to the frequency, that's a little harder. You play instruments. You think you can tell by your ear?
No.
Not very accurately. So we have technology that does that for us, and it'll be able to pull out that frequency. So something that like we do at work that sometimes that's sort of interesting is that I've worked on a project where, imagine this is a submarine. And what we have is a propeller at the end, we're turning around and around and around, and it's putting vibrations into this rod. Now, if some of those vibrations match the natural frequencies of this bar, it'll get louder and louder and louder. And that's really bad if you're living in a submarine. So they have to be very careful, and the same thing with you with your dune buggies, right? If something's vibrating and it matches one of the natural frequencies of the car, those vibrations will grow and grow and grow. What'll happen?
It'll break.
It'll break.
Okay, Jim, so I think I totally got it now. Okay, so you're saying that in the standing wave on this, that's going from back and forth, and it's standing because it's not running away. It's in this rod. And then you have a node in the middle where it's not where the vibration is being released, so it's still because they're canceling each other out. And then the frequency is the time it takes for the wave to go in 1 second. And then the wavelength is going to be twice the length of this because this is only the length of a half wave.
Yes!
Very cool. I like it. So now you know how to do it too, and you can be a master wave person. Thanks.
Thanks.